Hello, this is an orthogonal projection. I'm Rohit Vamuri, Spring 2022, Math 141, Section 2D. So let's get to it. So what is orthogonal projection? So before we know that, first know what are orthogonal vectors. Orthogonal vectors are basically whether two vectors are perpendicular. So in essence, if the dot product of the vectors are 0, then we know that they're orthogonal vectors. So orthogonal projection is basically just splitting up or decomposition of a vector into the sum of two orthogonal vectors. That's what we're doing. So an orthogonal projection could also be called as a projection for which the range and the null space are orthogonal subspaces, and orthogonal projection can also be part of a linear transformation. So it is a type of linear transformation. So now let's look at some images that might help clear the picture a little bit. So here we have the vector u being projected onto vector b, and so the resultant of that projection would be w1, right? So that is one way to do projection. So another one is the image right next to it. So we have it at an angle. This one is where v1 and v2 are both orthogonal vectors. So v1 is projecting onto v2, and so that pink line is that projection, right? So now let's go ahead and look at some formulas to basically help us better determine them. So here we have the formula. It's basically how like the normal projection formula is in previous topics. If you have covered that, if you have not, here it is. So the projection of vector v onto vector w, and you can see the illustration here as well that proves the point. So it's just the w times v over the magnitude of v squared times v, right? And so this is also one way to do it as well, with an angle in between, right? So to calculate that angle, we can also do u times v over the magnitude of u times the magnitude of v. So yeah, so now let's go ahead. We're going to go ahead and look at some example problems. We're going to look at two of them. So let's get to it. So let's do one. So the first one is finding an orthogonal projection of y onto the line of L, which L is just 3, 1. So we let A equals to 3, 1 transpose. So we want to use that projection formula, so which is A times A transpose A to the power negative 1 times A transpose times Y. So we can just do 3, 1 times the matrix 3, 1 times 3, 1 again. So you just have to know that they're transposed, and then basically just calculate from there, since those are, this nicely adds up to 10 because 3 times 3 plus 1 times 1, and then you multiply by 3, 1 times 2, 3, 2, 3, yep, 2, 3, yeah, makes sense. So now we're going to go ahead and make it equal to 3, 1 times 10 to 1 power, which is 1 over 10 times 9, which is 9 over 10, and we'll do 9 over 10 times 3, 1, which is that matrix, which is how we get 27 over 10 and 9 over 10. Okay. So we're going to look at example 2 now, right? And so with example 2, in the previous statement, in the previous problem, the previous problem, I forgot to iterate that y is equal to 2, 3, which is how we got this 2, 3 here. I forgot to write that down, but y is equal to 2, 3. So hopefully that clears that confusion. Sorry. But now let's look at example problem 2. So we have this as v equals 1, 0, 1, 1, 1, 0, right? And so we want to find the vector v in v, which is closer to y. So we know that that vector that we're trying to find is an orthogonal projection, v. So we want to put A as v1 slash v2. So v1 is 1, 0, 1, v2 is 1, 1, 0. Since the columns of A are the base of v, tells us that projection, right? So now let's go ahead and look at the calculation. So just A times A transpose A, 1, 0, 1, 1, 1, 0 times that, which is just equal to 2, 1, 1, 2. I'm not going to go over the exact mathematical calculations, but the formulas are what's more important here and applying them. So now just finding that inverse is how you do that, using the inverse formula, and then you just do A transpose times Y, which is just, remember, Y is 1, 2, 3 in this case, and A transpose is given to us already from the previous formula. which is just equal to 43. And so now we just basically combining all that information into that projection formula now. And so it's just 101, 110 times 113 and all this. So in the end, we'll get 7/3, 2/3, and 5/3. So now we should care about why we're doing this, for what purpose. So we can use orthogonal projection to help solve least squares projection, conditional expectations for multivariate normal distributions, Gram-Schmidt orthogonalization, QR decomposition. So all these topics that have been discussed can be used in real-world applications, and we'll look at how. So orthogonal projection can actually be used to compute the closest point on a curve or a surface. We can also use the formula to determine the projection formula to determine if something can stay in place or has to move out of the way for an object to pass through. So I think one real cool real-world application can be used here is that if a submarine is tracking a ship moving along a line and the range of a torpedo range is within half a mile, we can determine whether the submarine can stay where it is or if it needs to move out of the way to reach a place where the ship will pass within that range. So that can be really useful in military applications, and it can be used to solve linear regression problems or least square regression problems. So here's just a picture of this. Just a sample pictures to see. It's not super accurate to what's here, but just to get an idea of what this is, like a ship, and seeing if it's within that torpedo range. So yeah, that's about it. That's all. And here are the references that I've used here. So yeah, that's about it. Thank you so much for watching.